Hey everyone, my name is Sean, A+, Security Plus, and CCNA certified. Thank you for your consideration. Today I'm doing a Wireshark video, and I'm asking the question that actually matters. Is this problem on my side, the network, or is it the server? First we'll discuss plain HTTP, we'll find exactly where the delay is, and I'll show you how to measure server response time. Then we're going to go do the same thing with HTTPS. I'll show you that even though we can't see inside the tunnel, we can still find the latency. If it's applicable, we just have to know where to look. Alright, let's get into it. So let's open up our Wireshark. So this is a very simple HTTP TCP PNG file. And the problem is HTTP server web requests. The internet's not working. HTTP requests are taking a long time. What's the issue out here? Client complaint at 192.168.1.1. You can see that our server is 10.0.0.1. This is a very small PCAP file. Clear termination reset bit. And let's get analyzing with the data that we have. So is it the network? So where's the network? So the network is our SYN and our SYN-ACK, right? So we have client server, server clients at 97 microseconds. So that looks good. If that was a huge number, we'd pivot and we'd go down that road. However, that is not the case here. Everything looks good. Here's the ACK. And you can see here packet 4 we have our first HTTP. So this is the GET request from 192.168.1.1. We can see that here. It is indeed GET. Alright. And then you can see with these nifty tabs here on Wireshark that on packet 11 here, this is when the server responds with a 200 message. Okay. So we can see that. And what's important here, so Wireshark is great, and I'm still learning. I am still learning. I'm very much on the road to learning Wireshark. I'm just sharing what I know. So we have right here time since request. 1 minute and 40 round up 49 seconds. That's the issue. So from the server back to the client, from packet 4 to packet 11, it took 1 minute and 48 seconds. That's a long time to pull up a web page. And so what happened here? So basically we see all this TCP keep alive. So we have an acknowledgement here, and then all these keep alive. So 1495 sequence number, and then you can see here we have these 1 bits. So what are those 1 bits? Those 1 bits are some data which is 00. So they're basically like ghost bits. Basically this is the client and the server basically going, hey, we still doing this, we still doing this, we still doing this, and then here in packet 11 the server says, yes, we're doing this. However, that took a very long amount of time. If we didn't look down below, we could actually just kind of check it out. 45 seconds, 45 seconds, 18 seconds in our delta time process here. And we could see it that way in addition to. So that is, so to answer our question, where is the discrepancy? Or where's the problem in the network? So the network is definitely the server getting back to the client. So this is all great information. So what do we do with this? Wireshark is not going to fix this problem. So for a tier 1 level, what I would be doing is getting all the pertinent information. I'd be getting this PCAP file. I'd have packet numbers. I'd have IP addresses. I'd even have timestamps of what's going on here between the 2 packets, and I would put together a quick easy portfolio of all the information, and then send it to the relevant department. So, send it to a server team, whatever the case may be. Send it up the chain of command and get that ball rolling. But it would be my job here in Wireshark to gather as much information that's relevant as possible. Alright, so that's great for a very easy HTTP where we can see all this nice keep alive information and what's going on. However, what about HTTPS? So here we have another PCAP file. So this one's got a lot more going on. Let me just show some of the statistics. This is probably my favorite thing, is this bird's eye view of the networks. So actually I'll do this. So here you can see that we have all our endpoints. So all different types of endpoints, different cities. You can see I've set up geolocation for my Wireshark. So United States, even Japan, a lot going on. But what I really wanted to talk about was TLS. So you can see we start getting into TLS here. I'm going to find the first SYN bit, and we'll follow that. We're conversation filter, TCP. Alright, so now we have our network, SYN, SYN-ACK, and we're in purple territory here. Alright, so we can see if we go back to statistics, we could go to conversations, and a bunch of conversations, but now we have a display filter, so we're just between these two devices. Alright, which is just awesome. Alright, so we can see, so how's the network doing? So this is all, modern TLS encryption, all this stuff. We can still see here, what information do we have? We have our SYN, our SYN-ACK. So we can see that it was 28 microseconds. So that's kind of our baseline. We have 32, 27. We can kind of just see how the network's doing here. So 71, kind of up a little bit right there. That is something that we could jump into and look at. But really, we can scroll through. We could even go to time. What am I thinking? TCP. I'm thinking of something else. But we can check that out. What other information do we have here? We have some of the TLS. We have the TLS handshake. So here we have from the client, our client hello, and we have, of course, our timestamps. We have our TCP information, source destination port, flags. Gotta love the flags, right? Unskilled attackers spawn real security flaws. That is something you just can't forget. More importantly, we have our timestamps. So I'm going to set a filter for something that's important, especially in multi-thread environments, realistic multi-thread TCP stream environments. This is time since previous frame. We could set that as a column. And now we can follow individual TCP frames and see when the last packet was sent. Alright, so we have our hello, and then we have our server hello. And we can find out that information as well. TCP, we even have, our TLS stuff, ciphers, TLS 1.2, different information. If we were going from a security, we could see which cipher they chose to use together. All that. But we can see the distance. We can check out how the server is doing in this relationship via the time as well. And there's not like a huge discrepancy in time here. So really with this TLS, we're really looking at time. Time and source and destination. For example, this time since previous, we can filter by that. And if we go down to the bottom, we can be like, oh wow, 4 seconds for an application. And look at this, oh my goodness, it was the client. Well, this is where we have to be, this is where we have to think outside the box. So it'd be easy to be like, hey, look, there's some kind of problem with the client on the client side, right? However, this could be the client taking a little while just to put in a username or password. So we have to take into consideration client-side issues and client-side data. So what I'm learning is that we're really looking for patterns. So if it was like an isolated event, maybe they were doing something else, got back, and then okay, the TLS handshake application, whatever it was established, and everything was all good and gravy. However, if it was a pattern of events going on, pattern of events with these larger numbers, then maybe we'd have an issue. But not so much in this case. So actually in this packet, this TCP, this TLS, TCP, everything looks pretty good. But that's kind of how we check out the network here, our client server hello, and then how we can kind of see time since previous and follow individual TCP streams. You can see here, just to see kind of my Wireshark setup, I have a profile, Shark Tank, not the default, so this is kind of what I'm using to learn. I've set up different buttons so I can check out all the SYN bits and SYN acts and see where connections are happening. Errors, we can check out errors, bad packet drops, and go through those as well and look for large ones. Like see up here, we have a large duplicates and then intermittent ones. Or maybe no chatter, right? No chatter. So maybe we're on layer 2 and all the ARP, LDP, spanning tree protocol, all that kind of stuff, different filters. So this is something that I'm learning to put together better profiles for Wireshark for different circumstances. And that's something that I'm having fun learning as well. All right. So that's just a little bit about Wireshark, network troubleshooting, slow application, troubleshooting, and how you kind of look at that in a realistic way using either HTTPS or HTTP. So in HTTP, we identify the server response time by measuring the time between the client GET and the server response. The TCP handshake was clean, so the problem was conclusively the server side. And we talked about what that looks like in a real escalation workflow. What do we do with that data? In the HTTPS, we use the TCP SYN and SYNAC data to establish our network baseline, and then we measured the TLS handshake phases to identify server-side processing time, and we added the TCP stream delta column to isolate per connection timing in multi-threaded traffic. And we talked honestly about what we can and can't see in encrypted sessions. And the bigger takeaway, Wireshark doesn't fix anything, but it turns a vague complaint into a documented time-stamped packet level finding. And that is a completely different thing to bring to the table, to bring to a team, or bring to a vendor. Please check out the rest of my portfolio at SeanElgren.com, and I'll see you in the next one.